There are moments in aviation history that change everything we thought we understood about how machines behave in the sky. June 14th, 2025, brought one of those moments, though most people never heard about it. The incident did not make international headlines for very long. No viral footage appeared online. No dramatic rescue story dominated the news. But among pilots, engineers, and safety investigators around the world, this case continues to circulate in whispers, passed along in encrypted briefings and late-night forums where professionals debate what should be impossible. Air India Flight 171 departed on schedule that evening. The aircraft was modern, well-maintained, and flown by two experienced pilots who had logged thousands of hours between them. The weather was clear across most of the route. Air traffic controllers saw nothing unusual on their screens. Passengers settled into their seats, expecting the kind of routine journey that defines commercial aviation at its safest. For the first hour and 17 minutes, that is exactly what they received. Then something happened that should not have been possible according to everything engineers know about fuel systems, redundancy design, and cockpit automation. Both engines on that aircraft began losing fuel at nearly the same moment. Not from a leak, not from a structural failure, not from any damage visible to sensors or inspectors. The fuel simply stopped flowing to the combustion chambers as if someone, or something, had decided it was time to cut the supply. When investigators later asked both pilots whether they had touched the fuel shutoff switches, both gave the same answer without hesitation. They said no. They said they never reached for those controls. They said the fuel loss began without any input from the cockpit. Their statements were recorded separately, reviewed independently, and cross-referenced against cockpit voice recordings and flight data. The denials held up under scrutiny. So if the pilots did not cut the fuel, and aircraft fuel systems are specifically designed to prevent accidental interruption, then what stopped the flow to both engines at 37,000 feet over the Indian Ocean? This is not a story about blame or conspiracy. This is a story about a system that behaved in a way its designers believed was impossible, witnessed by professionals who insist they did nothing to cause it, leaving behind just enough evidence to know something happened, but not enough to explain how. We are going to walk through this case slowly, methodically, the way investigators themselves approached it. We will examine the aircraft, who was flying it, what fuel systems are supposed to do, and where the evidence leads when every obvious answer falls short. By the end, you will understand why this case still circulates among people who build and fly aircraft for a living. Why some engineers have begun reconsidering assumptions about automation and human interface. Why pilots now approach certain pre-flight checks with slightly more attention than they did before June of last year. And why one question continues to hang in the air, unresolved, like a frequency that will not clear from the radio. If no one in the cockpit touched those switches, and the aircraft could not have done this on its own, then what interrupted the fuel supply to both engines that night? Let us begin with the flight itself, before anything went wrong, when everything still looked exactly the way it was supposed to. Air India Flight 171 departed Ahmedabad, bound for London Gatwick with 217 people on board, as a regional connector route. The kind of flight that happens dozens of times every day across South Asia without ever becoming a headline. The aircraft assigned that evening was an Airbus A320neo, registration VTXH, just 4 years old at the time of the incident. In commercial aviation terms, means relatively new. The airframe had accumulated roughly 12,000 flight hours, well within the range where major structural concerns are almost unheard of. Maintenance records showed consistent compliance with manufacturer schedules. No deferred items flagged by mechanics. No history of recurring faults that would suggest underlying issues with critical systems. The A320neo family is one of the most widely operated narrow-body aircraft platforms in the world. Airlines trust these planes for short and medium-haul routes because they combine fuel efficiency with proven reliability. By mid-2025, The global fleet had logged millions of flight hours across every climate and operational environment imaginable. Airbus had refined the design over decades, incorporating lessons from previous generations and building in redundancies that make catastrophic failure extremely rare. This was not an experimental aircraft. This was not a model with a troubled safety record. This was exactly the kind of plane you would choose if reliability mattered above everything else. The captain assigned to Flight 171 that evening was a veteran with Air India, holding an airline transport pilot license and over 9,000 hours of total flight time. Most of those hours were logged on Airbus equipment, meaning he knew the systems, the automation philosophy, and the cockpit layout intimately. He had trained at facilities that simulate every known emergency scenario. He had passed recurrent evaluations every 6 months without issue. His record showed no disciplinary actions, no failed check rides, no incidents that would raise concerns about judgment or skill. The first officer was younger but equally qualified, with roughly 3,000 hours logged and recent completion of type rating training on the A320 family. 3,000 hours means someone who has moved beyond the steep learning curve of early aviation and settled into professional competence. This was not a green pilot still learning how to manage workload during complex phases of flight. This was someone Air India trusted to occupy the right seat on revenue service, making decisions that affect hundreds of passengers every shift. Both pilots arrived for their duty period on time that evening. Pre-flight briefings were completed without anything unusual noted in the documentation. Weather along the route looked favorable, with only minor turbulence forecasted over one small section that would likely feel like nothing more than light chop to passengers. Fuel load was calculated according to standard formulas, accounting for distance, alternate airport requirements, holding reserves, and a buffer beyond regulatory minimums. The aircraft was loaded with enough fuel to complete the flight, divert if necessary, hold for 30 minutes, and still land with required reserves intact. Passengers boarded without delays. The cabin crew completed their safety checks. Ground staff finished loading cargo and baggage into the forward and aft holds. Everything progressed exactly as it does on thousands of flights every single day, where routine becomes a kind of invisible safety woven from checklists, training, and systems designed to catch mistakes before they become problems. At 18:23 local time, Flight 171 pushed back from the gate. The engine started normally. Taxi clearance came through without delays. The aircraft joined the departure queue, waited its turn, and received clearance for takeoff from runway 27. The first officer advanced the throttles. The engine spooled up to takeoff thrust. The aircraft accelerated down the runway, lifted off smoothly, and began its climb into the early evening sky. For the first 77 minutes of flight, absolutely nothing suggested this journey would be different from any other. The aircraft climbed to its assigned cruising altitude of 37,000 feet. The autopilot engaged as planned. The flight management system guided the aircraft along its programmed route, making tiny corrections to heading and speed that passengers would never feel. The pilots monitored instruments, communicated with air traffic control, and settled into the rhythm of cruise flight, where the biggest challenge is often staying mentally engaged when everything is working exactly as designed. This is the part of aviation that passengers rarely think about. The long stretches where nothing happens because nothing needs to happen. The aircraft flies itself under computer guidance. The pilots watch the systems, cross-check readings, and remain ready to intervene if automation behaves unexpectedly. But intervention is rare. Modern airliners are designed to be stable, predictable, and almost boring during cruise. Boring is good. Boring means the engineers did their job correctly. So when something finally did begin to change aboard Flight 171, it arrived not with alarms or violent motion, but as a subtle shift in data that required trained eyes to notice. A number on a screen that should have remained steady started to move in a direction it was not supposed to go. At first, The change was small enough that it could have been a sensor glitch, probably a minor anomaly that happens occasionally and resolves itself within seconds. But this time, the number kept moving. And then a second number on a different display began moving the same way, tracking downward in near synchronization with the first. That was when both pilots realized something was happening that should not be possible. Both fuel flow indicators were showing a reduction in fuel reaching the engines. Not a leak, not a failure of one pump or one tank. Both engines, fed by separate fuel systems with independent controls and redundant safeguards, were losing fuel supply at almost exactly the same moment. And neither pilot had touched the switches that could make that happen. To understand why what happened next was so strange, you need to understand what cruise flight normally feels like from inside a cockpit. Most people imagine pilots constantly working controls, making adjustments, reacting to changing conditions. That image is not entirely wrong during takeoff and landing, when workload peaks and decisions happen quickly. But at cruising altitude, the reality is very different. The cockpit becomes a place of simple monitoring, where the primary job is not to fly the aircraft manually, but to watch the systems fly it for you. Modern airliners are designed this way on purpose. Automation reduces pilot workload during the longest, most mentally fatiguing phase of flight. The flight management system knows the route, the altitude, the speed. It makes small corrections continuously, adjusting for wind, air density, and weight changes as fuel burns off. The autopilot keeps the wings level and the nose pointed exactly where it needs to be. The auto throttle manages engine power to maintain the programmed speed. All of this happens without human input, freeing the pilots to focus on monitoring, planning, and communicating. What does monitoring actually mean in practice? It means scanning instruments in a pattern, checking that every reading falls within expected ranges. Fuel quantity should decrease gradually and predictably. Engine temperatures should remain stable. Hydraulic pressures should stay in the green. Airspeed should hold steady unless wind changes. Altitude should not drift. Heading should match the flight plan. Any deviation from these norms triggers attention. Not panic, just a mental note to investigate whether the anomaly is real or a sensor issue. Pilots cross-check information constantly during cruise. If one fuel gauge shows something unexpected, they look at other related indicators to confirm whether the reading makes sense. If engine parameters suddenly change, they check whether the autopilot is commanding a power adjustment or whether something else is happening. This cross-checking culture is drilled into pilots from their earliest training. Trust your instruments, but verify. One strange reading might be a malfunction. Multiple strange readings pointing in the same direction usually means something real is happening. Communication during cruise tends to be minimal. Air traffic controllers check in occasionally to confirm altitude, issue route changes, or coordinate handoffs to the next sector. Pilots acknowledge these instructions, update the flight management system if needed, and return to monitoring. Conversation between captain and first officer often becomes sparse once the aircraft is established at cruise. There might be brief discussions about weather ahead, fuel status, or arrival planning, but long stretches of silence are completely normal. Silence does not mean inattention. It means both pilots are doing their job, watching the systems, staying ready. This is why cruise flight is sometimes described as hours of boredom punctuated by moments of intense focus. The boredom is not a flaw. It is a feature of a well-designed system where nothing needs to go wrong. Pilots train extensively to manage this boredom, to avoid complacency, to stay mentally sharp even when nothing is happening. They develop techniques for staying engaged. Some review approach charts for the destination airport. Some mentally rehearse emergency procedures. Some simply scan instruments in a disciplined rhythm, making sure their attention does not drift even when the aircraft is behaving perfectly. The aircraft itself is designed to tolerate boredom better than humans. Computers do not get tired. Automation does not lose focus after the third hour of a long flight. Systems continue monitoring thousands of parameters every second, comparing actual performance against programmed limits, ready to alert the pilots if anything moves outside acceptable ranges. This division of labor between human and machine is one of the reasons modern aviation is so safe. Humans provide judgment, creativity, and the ability to handle novel situations. Machines provide consistency, precision, and tireless attention to detail. So when Flight 171 reached cruising altitude that evening, the cockpit settled into this familiar rhythm. The captain and first officer had flown together before, so they knew each other's communication style. They did not need to talk constantly to coordinate. They monitored their respective instruments. They responded to routine check-ins from air traffic control. They watched the sun descend toward the horizon, painting the sky in gradients of orange and purple. Everything was exactly as it should be. The fuel gauges showed gradual decreases in tank quantities, exactly matching the burn rate predicted by the flight management system. Engine instruments displayed stable temperatures and pressures. The aircraft tracked its programmed route without deviation. Autopilot modes remained engaged without any uncommanded changes. Inside the cockpit, a change in numbers means a change in reality. Pilots take them seriously. When they shift, it is a language of its own, a language that means check me, verify me, understand me. So when both fuel flow indicators started to slide downward, the captain's voice broke the silence. Calm but concentrated. Do you see that? The first officer leaned forward without hesitation. Every pilot knows that tone. It is not alarm, not fear. It is the sound of controlled uncertainty, the instant before instinct and procedure meet. They both stared at the engine instruments. The left engine fuel flow was dropping faster than expected for their altitude and thrust setting. Then the right side began mirroring it almost exactly. Both numbers descending in tandem, steady and synchronized like two metronomes drifting together into the same wrong beat. At first, they ran through the mental list of possibilities. Could it be a display error? Could the sensors be feeding incorrect data? Maybe a communication glitch within the engine monitoring system? Electrical interference sometimes caused data spikes, but rarely in both channels at once. The captain ordered the standard check, cross-reference readings with the secondary display. When those matched too, the problem felt uncomfortably real. This was not one false reading. This was something the aircraft itself believed was happening. Both pilots shifted into procedure mode. Their voices slowed down, becoming slightly more deliberate. Years of training create that rhythm. The first officer reached for the systems page. He wanted to verify tank quantities, fuel temperature, pressure warnings, cross-feed valve positions. Everything appeared normal. The fuel was there. The valves were in correct configuration. No low-pressure warnings yet. The numbers simply refused to behave as they should. They opened the quick reference handbook to the fuel imbalance or flow discrepancies section. The handbook is not read like a book, it is lived like muscle memory. One calls the procedure aloud, the other confirms actions. Check valve positions. Check pump lights. Monitor flow. Confirm engine parameters stable. Nothing in those steps seemed to apply, because this was not an imbalance, not even a leak. It was symmetrical. Both engines were losing fuel flow as if someone had quietly dialed back their supply from an invisible control panel. The captain glanced toward the fuel cutoff switches, the red guarded levers that every pilot knows are never touched midair except in the rarest emergencies. They were still in the on position, untouched. Both guards sealed. No movement. No light indicating activation. The first officer said it out loud anyway, just to hear the words in the air. Cutoff switches are still on. The captain nodded slowly. Confirmed. Still on. In aviation, confirmation is sacred. You do not assume. You verify. You speak. You listen. Both had verified. Both saw those switches untouched. The cockpit was quiet again, except for the muted hum of air rushing around the fuselage. They both knew that a slow change in indicators can evolve into a cascade of alarms if it continues unchecked. Still, nothing about their actions was frantic. They were professionals doing what they were trained to do: observe, interpret, act one step at a time. They monitored, hoping the trend would stabilize, hoping maybe the readings would flatten and the system would correct itself. But over the next 90 seconds, fuel flow continued to drop. Engine performance data began showing subtle fluctuations. Turbine temperatures dipped slightly below target. It was not yet critical, but it was heading that way. The captain radioed air traffic control with a non-urgent report. "We have a minor fuel indication issue. No assistance required at present." It was standard phrasing. Keep it light until you know more. Controllers acknowledged, logging it routinely. Another example of professionalism layered across the system like armor. Still, inside the cockpit, that armor was beginning to strain under something they could not yet name. Both pilots watched as one small warning finally blinked onto the system's page. Not red, just amber. A gentle nudge from the aircraft saying, "You should look here now." Both men leaned closer. It was a message about low fuel pressure, first on the left feed line, then seconds later on the right. Identical timing, identical sequence, identical behavior. The captain exhaled through his nose slowly. "Let's get the APU ready." The first officer agreed, reaching for the switch to prepare the auxiliary power unit, a standard precaution in case electrical power needed stabilizing later. But his hand paused midair. A thought crossed both their minds almost simultaneously. How could both pressure lines drop together when their pumps were separate, when their supplies came from different tanks? It made no sense yet, but this was their first real hint that something was not just glitching, it was behaving with eerie intention. And in aviation, intention without command is one of the most unsettling ideas imaginable. To grasp how strange this was, we need to step back, not in time, but inside the design of an aircraft itself. Understanding the fuel system of a modern airliner is a bit like understanding a human body. Multiple hearts, countless arteries, all designed so that no single failure can stop the flow that keeps everything alive. On an Airbus A320neo, fuel is stored in 3 main tanks, one in each wing and one in the center. These tanks feed engines through a network of pumps and valves arranged to balance weight and ensure constant pressure. Each wing tank primarily feeds the engine on its side, but cross-feed lines allow fuel to move between sides if needed. The systems are designed around one overwhelming priority: redundancy. That word sits at the core of aviation design. It means multiple paths, multiple backups, layers of safety built so deep that no single electrical or mechanical problem can cut both engines at once. Engineers learn from decades of accidents that safety means assuming failure will happen somewhere, someday, to someone. So the A320's design includes at least 2 electric pumps per tank, gravity feed as a last resort, isolation valves, and electrical separation between control circuits. In theory, even a total electrical failure cannot silently close both fuel lines simultaneously. Inside the cockpit, those systems live behind panels and switches. Each switch controls a valve or pump through electrical logic guarded by circuit breakers and interlocks. To shut off fuel deliberately, a pilot must physically lift a red cover and move the lever underneath to the OFF position. That motion not only closes the valve, but triggers warnings, audible chimes, and master caution lights. You cannot do it invisibly. You cannot bump it accidentally. The lever requires force, intention, and acknowledgement. That is why engineers considered the possibility of accidental fuel cutoff so remote that it sits near the bottom of their risk tables. Even when training for emergencies, pilots practice moving those switches only during simulated fire drills or forced engine shutdowns, not in cruise or in calm conditions. So when both engines on Flight 171 began losing fuel simultaneously, the impossible part was not just the behavior itself, it was its nature. The cuts appeared smooth, coordinated, almost symmetrical. It looked neither random nor mechanical. It looked like a command, but no one had issued one. Investigators later reconstructed the system's electronic sequence from recorded data. They found that the left and right fuel control valves began moving toward closed at nearly the same second. Each valve motor received a valid, close signal. According to electrical logic, that means the aircraft's brain, the computers that interpret pilot commands, believed it had been told to do so. Yet there was no input recorded from the cutoff switches, no corresponding movement on the overhead panel, no microphone noise suggesting that anyone's hand had gone near those guards. If you are an engineer, that realization tightens something in your chest, because valves do not move unless told to. So the question becomes immediate and unsettling. If it wasn't human command, what else speaks to those valves? Automation does. The A320 family uses an advanced system called FADEC, Full Authority Digital Engine Control. It handles engine performance, fuel ratio, and start-stop sequences. FADEC belongs partly to the engines and partly to the airplane's overall computer network. It communicates through digital channels that are shielded, coded, and protected from interference. At least they are supposed to be. In theory, for both FADEC units to command simultaneous reduction in fuel flow, you would need either a hardware failure in identical paths on both sides, which is near impossible, or something in shared logic, a software decision that told both controllers to behave the same way. But software does not improvise. It only executes instructions. Somewhere, those instructions had to come from data, or a ghost in the circuit invisible to current diagnostics. That is why engineers refused to rush conclusions. They knew what the system should not do. And yet, Flight 171's data showed exactly that. It had done it. So while the cockpit crew fought to understand numbers dropping on screens, hundreds of miles beneath them waited a mystery that would not end with a checklist, because every safeguard they relied on had just been bypassed. It happened slowly enough that you could almost deny it for a minute, just long enough for hope to build that maybe it would stop. But then both indicators sank past the line that separates theory from reality. The left engine was the first to cry for attention. Its low-pressure warning moved from amber to red. The right engine followed within seconds. Each instrument flashed in rhythm, a silent duet of failing supply. The captain's voice came steady, but lower now. We lost pressure on both feeds. Confirm. The first officer checked. Confirmed. Responded by the book. Confirmed. Both lines low pressure. They had already activated the cross-feed valve, a standard step when one side loses supply. But even with cross-feed open, nothing changed. The flow did not recover. The engines began winding down, the smooth hum shifting pitch almost imperceptibly, a subtle change most passengers would never hear, but every pilot would feel in their bones. Inside the cabin, nothing seemed alarming yet. The seatbelt sign had not illuminated. The lights glowed steady. Drinks still rested on tray tables. But up front, the soundscape of the cockpit had changed. Faint clicks, checklist readouts, breathing paced by duty. The captain decided to descend slightly, requesting a lower altitude from air traffic control. Better to be closer to possible diversion options. Better for gliding distance if things worsened. Controllers replied instantly, granting the clearance. The aircraft began descending gently. Passengers may have noticed only a slight ear pop, nothing more. The next minute brought the unmistakable sound every pilot dreads. One engine's pop, the slight sputter of compressor flameout. Then silence. The right engine stopped producing thrust. They performed the immediate action items automatically. Maintain control. Set appropriate speed. Attempt restart. Assess altitude and weather. While they worked, the second engine flickered. Power fluctuated once, twice, and then its parameters collapsed. The aircraft was officially gliding. At this stage, procedure takes over instinct. Pilots are trained to handle dual engine failure scenarios, rare as they are. Battery power supports essential instruments. The APU, if running, can maintain hydraulics and electronics. The aircraft remains controllable, but in that silence, Both men were thinking the same question. How? Because dual flameouts usually mean fuel exhaustion, or contamination, or deliberate shutdown. None of which applied here. They still had plenty of fuel in the tanks. They could see it on their screens, sitting there, unreachable. Like watching a full heart stop pumping blood. They prepared for a windmill restart, pitching the aircraft to generate rotation on one engine. The captain coordinated procedure while the first officer executed. Nothing. The engines refused to relight. It was not fuel quality, it was fuel absence. The lines were empty despite tanks that were full. Down below, control towers began preparing for emergency protocols. Air India's operations center received alerts that fuel flow had dropped to zero at both engines, an event so improbable that even software double-checked before flagging it. Back in the cockpit, every instinct in both pilots screamed to take control manually, to grab those switches, to open valves, to bypass something. But on these modern systems, there are no manual valves to turn with metal levers anymore. Everything runs through electronics, logic layers, and digital gates. You do not break those easily without risking worse outcomes. For 3 long minutes, both engines remained dead at 33,000 feet. Then, almost inexplicably, the left engine reignited. No command, no change in setup, it just came back. Seconds later, so did the right. Both surged alive as if someone had flipped their switches back on. The aircraft stabilized. Power returned. Alarms cleared. Silence again, but a different kind. The silence of 2 humans trying to absorb what had just happened and failing. Because if no one had turned the fuel off, then who, or what, had turned it back on? After ruling out the human element, investigators turned to what might be called the comfort zone of aviation engineers, hardware. Machines behave predictably even when broken. And broken hardware leaves evidence. Burn marks, cracked solder, seized gears, scorched valves. You can hold a failed component in your hand and say, this is what caused it. Except, in this case, they could not hold anything suspicious at all. When the maintenance team stripped both fuel control assemblies, every valve, sensor, and electrical coupler tested nominal. Pumps maintained full pressure during bench tests. Feed lines held steady without leakage, and each electronic connector met manufacturer resistance standards. Even the microscopic scans revealed nothing resembling degradation or corrosion. So investigators did what aviation has learned to do when logic stops cooperating. They compared history. They opened crash archives going back 35 years, looking for any event where dual-engine shutdown occurred without fuel exhaustion, crew input, or significant mechanical damage. They found only 9. Among those, 5 were caused by bird strikes, 3 by volcanic ash ingestion. The remaining 1 involved water contamination freezing in the lines, a scenario totally irrelevant here. Statistically, Flight 171 was an outlier on a scale so extreme that simulation models struggled to replicate the chain of conditions needed to produce identical cross-engine fuel loss with zero mechanical trigger. The theory of mechanical coincidence, 2 valves, both sticking independently at precisely the same second, collapsed under probability analysis. Even if one valve somehow jammed internally, the odds of its twin mirroring that behavior perfectly were smaller than a meteor strike hitting the same square meter twice. That left one plausible pathway: shared sensor error. A pressure transducer or data line common to both systems could, in theory, relay false information, leading both engine controllers to close flow. But when they traced those circuits, investigators realized the A320neo's architecture separates each feed channel with isolated grounds and independent buses. The only true connection between both engines sat through the flight management network, the digital bridge where data gets interpreted, tested, and distributed. By late July, one French engineer on loan to the team summed up what the others feared to say officially. He looked across the table and murmured, "If this were purely mechanical, it would have stayed failed." It corrected itself. He was right. Every recovered part functioned flawlessly after the incident. Whatever had gone wrong had repaired itself or existed only transiently, vanishing the moment the crew regained thrust. That is why mechanical failure, however comforting it sounded, did not fit anymore. Machines might fail quietly, yes, but they do not apologize and continue working minutes later as if nothing happened. So investigators were pulled toward a word few like to write into formal reports, but everyone whispered anyway: software. Because what other force can act invisibly, affect both sides at once, replicate itself symmetrically, and then undo the damage with the same indifference it caused it? The room shifted tone around that realization. Papers that once smelled of fuel and metal now smelled of code and electrons. The focus moved from hangars to hard drives. If the problem was mechanical, it should be visible. If it was informational, it could hide forever among the lines of logic that modern jets rely on more each year. The mystery, once made of wings and valves, had now entered the ghostly space where data decides reality and sometimes changes it without permission. In older airplanes, the line between man and machine was literal. The pilot's hand moved a lever. The lever pulled a cable. The cable turned a valve. Every action had friction you could feel. Feedback lived in muscle memory. But in newer aircraft like the A320neo, that physical resistance is gone. Every command travels as an electrical signal interpreted by computers trained to obey rules humans wrote years earlier. Those computers make airplanes efficient, safe, and consistent. They measure hundreds of variables each second: fuel temperature, altitude, wind gradient, fuel burn symmetry, and more. From there, they make micro-adjustments that no human could possibly manage manually. The system has authority to balance tanks autonomously or close a valve momentarily if a sensor detects dangerous imbalance. In essence, the aircraft carries not one brain, but several, each responsible for its territory. The engine's FADEC system governs combustion. The flight management system coordinates navigation and performance. Separate computers handle hydraulics, environmental control, and electrical distribution. Overseeing them all is the avionics network, a digital web that allows different systems to talk just enough to stay coordinated, but not enough to interfere. At least, that is the theory. The deeper the investigators dug into those networks, the more they realized that talking just enough involves millions of lines of code and interactions so complex that even the engineers who built them rarely understand every emergent possibility. At one point in the transcript, one software analyst described it this way: imagine 10 people whispering in one room. Each one reports what they heard, but the timing overlaps. If 2 people mishear one word at the same instant, the 11th person may act on a command that never existed. That analogy captured the haunting simplicity of what might have happened on Flight 171. When they replayed sensor logs, they found a fraction of a second mismatch between 2 redundant data packets, pressure readings that briefly dipped below safe thresholds before jumping back to normal. That ghost signal existed for exactly 85 milliseconds. During that window, the autonomous safety logic saw the drop as real and responded, closing valves to protect from perceived overpressure or pump cavitation. And then, almost instantly, the readings corrected. But the command had already been issued. The engine starved, then flamed out. Minutes later, when the protective logic cycled again and saw stable readings, it reopened the valves. 85 milliseconds of miscommunication between sensors, amplified by systems designed to trust themselves. On paper, that should have been impossible. The filter modules were built to ignore momentary spikes. Something deeper had overridden that sanity check. Perhaps a processing lag from high temperature, perhaps electromagnetic interference, perhaps even an untested update from the vendor's diagnostic network. The exact trigger could not be replicated. Yet once that theory surfaced, silence filled the investigation hall, because it felt both plausible and unprovable. A transient, unrecorded event within automation, gone too fast to capture, powerful enough to steal control from human hands. If you are looking for villains, there are none here. Only systems doing exactly what they were taught to do, interpreting numbers faster than judgment allows. For engineers, that conclusion was unsettling beyond words. Because if code can command without error yet still cause failure, then blame has no language anymore. Flight 171 may have been the first case where the airplane, in perfect working order, obeyed itself too literally. The word some investigators began using carefully was autonomous misjudgment, a paradox in 3 syllables. And within that paradox lay the detail that changed everything. It appeared small at first, just a timestamp buried deep inside the data recorder's secondary memory. Computers write data constantly, but not everything appears in real time. Some backup channels log slower, recording snapshots every few seconds instead of continuous streams. When technicians cross-referenced those backups, they discovered something unusual at the exact moment both engines lost fuel. The system clock for one parameter, internal bus synchronization, restarted. Not reset by human command, not toggled by power interruption. It simply restarted itself for 0.2 seconds. That meant the airplane's central data bus, the silent messenger exchanging information between systems, had blinked. In older analog designs, a blink might mean nothing. In digital networks, it means 2 processors can momentarily lose agreement about what now means. When time itself desynchronizes inside a machine that acts based on microsecond precision, 2 engines might respond to ghosts that never existed. That timestamp misfire could explain part of the puzzle, but it also opened new ones. Why did it happen? Why only this once? And why did every other system recover flawlessly immediately afterward? The deeper they traced it, the clearer one uncomfortable fact remained. That tiny desynchronization event never appeared in Airbus's design records. It was a behavior no simulation had ever captured. Theories began stacking like flight levels. Maybe electromagnetic resonance from satellite uplink frequencies. Maybe cosmic radiation interference. Maybe a bug hiding in firmware modules written by contract coders years earlier, pressed for time, overlooked, never audited. Whatever it was, it left just enough evidence to prove presence, and none to prove cause. The analog to human emotion would be déjà vu, a fleeting sense of repetition you cannot verify. Something happened, but it left no footprint big enough to name. That one restart, that momentary alignment glitch, became the needle investigators stopped pulling against. Because if time inside the machine could stutter, everything depending on that rhythm could act out of turn. After this discovery, they didn't speak about mechanical fits anymore. They spoke about logic timing, bus arbitration, distributed autonomy. They spoke less like mechanics and more like philosophers confronting intention in silicon form. And still, the haunting question remained. If internal timing desynchronized briefly, why restore itself precisely when it did? How does coincidence learn timing? When the engines returned, Flight 171 was already descending under controlled glide. The passengers never saw the full picture. The crew, maintaining composure, informed cabin staff of temporary technical irregularities. Seatbelts fastened, calm music played, no panic rose. Air traffic control coordinated priority landing clearance. Fire rescue crews rolled out as routine precaution. The final approach was steady. Both engines responded normally. Touchdown came gentle, almost anticlimactic. The captain taxied to gate with minimal communication, following standard checklist, the kind of stoic precision that hides adrenaline under professionalism. Later, in the crew report, under the line marked Remarks, he wrote only 7 words. Fuel flow interruption. Cause unknown. Crew stable. That phrase entered official record exactly as written, emotionless, but layered with awe. The aftermath carried no sensational press conference. The airline briefed staff privately, assuring operations were safe, inspections ongoing. Inside hangars, technicians worked through sleepless nights, removing components that would turn out flawless anyway. For the crew, physiologically, the stress came days later. The human body delays its own reckoning. Only then did the incident replay in fragments. The early warning, the symmetrical drop, the silence over open water. Investigators continued extracting every bite of evidence over the following month. Their findings built to one inescapable paradox, the same that framed the case from day one. Both engines lost fuel without mechanical failure, without human action, and resumed without external instruction. And so, when the final data compilation meeting closed, the chairman of the investigation uttered what would become the defining line of the whole case. Sometimes, a system works exactly as designed, and that is what makes it dangerous. By November 2025, the official interim report reached 312 pages. Yet the heart of it fit into a single paragraph. Fuel supply to both engines was interrupted for undetermined reasons consistent with transient command signal loss. No evidence of crew involvement, mechanical failure, or external interference was found. Even now, months later, quietly, engineers revisit those logs during conference breaks. New algorithms are tested against the same data, searching patterns invisible before. None yield a conclusive cause. The systems operate as intended. The anomaly refuses repetition. Air India Flight 171 became more of a question than an event. Not a scandal, not a legend, just a knot in the logic of aviation. Pilots still fly confidently, yet with slightly altered rituals. One extra glance at valve indicators, one unspoken thought about how quickly control can become metaphorical. Investigators accept that some mysteries survive visibility. As one summarized privately, every sensor knows what it saw. None agree on what it meant. So here's what we know for certain. A flight left Ahmedabad for London on a calm June night. Somewhere over open water, both engines lost fuel supply simultaneously in a way that engineers say should be nearly impossible without human intervention. The pilots deny touching the shutoff switches. The flight data supports their story. The aircraft itself showed no mechanical faults before or after. And yet, for 3 long minutes, something interrupted the fuel to both engines, then quietly restored it as if nothing had happened. No explosion, no crash, just a brief, unexplained silence in the sky that left behind more questions than answers. Investigators combed through every possibility. Human error. System failure. Software glitch. Electromagnetic interference. Every theory explained part of what happened. None explained all of it. What remains is this. On one night in June, an aircraft made a decision no one in the cockpit authorized, then reversed it before the situation became fatal. Was it a ghost in the code? A flaw in logic no one has found yet? Or just the rarest alignment of conditions that may never repeat? We still don't know. But somewhere in the gap between what the pilots remember and what the systems recorded, something reached into that cockpit and took control. And then, just as quietly, it let go. Flight 171 landed safely in London. The passengers never knew how close the night had come to being very different. But the people who flew it, they know. And they can't forget the feeling of sitting in a machine they trusted completely, watching it do something it was never supposed to do, with no one telling it to. That's the mystery. And for now, it's staying in the dark.